Okay, hello everyone. Welcome to this session on reactive integration with Akka Streams and Alpakka. My name is Jacek Kunicki. I work at Software Mill. We're a company that basically writes code, so this is not really unique about us, but there are some other things that are actually unique. Those two are that first of all we work remotely, so we don't have an office, and also we have a flat internal structure. So if you would like to learn more about it, please feel free to either catch me after the talk or visit our booth here at the conference. So speaking of the topic of this presentation, integration between systems, this is actually something that is probably the most common programming task that you do, which is processing data, which means that you have some data that is incoming, you do something with the data, and you output it somewhere else. And if you think carefully about system integration, this is actually what it boils down to. So this is actually very simple, but there are different ways to do it. So if you look at the history, how we used to do it previously, well, around the year 2000, there was a small breakthrough in how we build distributed systems under the name of service-oriented architecture and web services, which basically meant that you are dividing your systems into smaller services that are somehow communicating between themselves. The way for them to communicate was something called an ESB, or Enterprise Service Bus. And if you looked at this architecture, how it worked and what problems it had, well, it seemed nice, but the problems that there were, for example, you didn't have something like service discovery, which we normally use today in the world of microservices. You didn't actually have any testing tools for that, so this is, well, if you tested it somehow, it was nice, but there was no support from testing frameworks to do it. And also the systems that were implemented, like the services themselves, were actually usually synchronous and blocking, so all the processing was not done in an asynchronous fashion. It basically blocked. Nevertheless, this entire concept was converted to some specifications and some design patterns. In 2003, we had a book called Enterprise Integration Patterns, which is, if you heard about the design patterns from Gang of Four, this is something similar, but in terms of distributed software. And although there were some problems with that, it became so popular that it has been implemented as Apache Camel, so the framework that you probably know if you have ever dealt with systems integration. So Apache Camel was, and probably is also now, the de facto standard for integrating different systems. The great thing about Apache Camel is that it can connect to almost anything. I mean, if you name a system, there is probably a connector to it in Apache Camel, but it also has some problems, so it's not perfect. And apart from the problems I described in general about the web service approach with the ESB, there are some others. So, well, Apache Camel is also synchronous and blocking. So most of the connectors that you have in Camel are synchronous and blocking. This is actually not entirely true, because there are some components that can be asynchronous, they can be reactive, but still overall the entire framework is blocking, so even if and synchronous. So even if you have a single component that is asynchronous, the framework itself would still block somewhere. Another bad thing about Apache Camel is the fact that it is so-called stringly typed, so basically you don't have any compiler that is guarding you against sending data of wrong type from one connector to the other or throughout the bus, because you're basically sending strings, and then they are decoded somewhere, but as you know, this may result in some kind of weird runtime exceptions. So if we look at how data processing has changed over the years, well, first of all, today we are mostly not dealing with batch data, but we are dealing with streams of data. So, and streaming data in this case, meaning having some possibly infinite source of data that you need to process on the fly. So it's no more loading data once, doing something with that and storing it somewhere else, but the data is coming in constantly, and you need to deal with it as it comes. Also, in such streaming scenarios, it's very important to be able to handle flow control somehow. And the most important thing is not to flood the consumers, because if you imagine that you have a producer of data that is very fast and the consumer that is very slow, there is some excess data, and if there is too much of this excess data, the consumer can get flooded somehow, and this is not what we want to have. Another thing that becomes important when working with such streaming architectures is an easier programming model. So it would be nice if you would be able to really define easily all those data processing steps for the data you're dealing with. And if we go back to this very simple programming task, boiling down to processing data, and if you think what's inside this box that does something to your data, well, you have something that comes in and something that comes out. So if you think of it, this is actually applying function to your some kind of function to your data. And speaking of the easier programming model, we can actually get a bit close to functional programming and to being able to express these integration patterns. So the way we handle our data with functions and with function compositions, because if you have a number of steps that do something with your data, and each of this step is a function, then you're basically composing the functions that you're applying to your data. So something has changed, and the way we can try to do it these days, with all those previous points in mind, can be done with the help of project Alpakka. Which is basically a set of connectors to different data sources, destinations for Akka Streams. Akka Streams being one of the implementations of the Reactive Streams approach to data processing. I will cover this in short in the next slides. So this is basically a set of connectors. It is certainly not so widely known, I think so, at least not so widely as Apache Camel. And it has a lot of much less connectors. So Apache Camel had around 200, Alpakka has around 30, at least at the moment. But it has some great advantages over Camel. First of all, it is non-blocking, and it's built in a non-blocking fashion from scratch because it's based on the Reactive Streams approach. It has the Reactive Stream concepts built in. And then also you get type safety. So this was not the case with Apache Camel, because then you got this stringly typed data. Here you actually have the types of your data defined. They are verified by the compiler, so the compiler guards you from sending data of wrong type. So if we come back to stream processing and see what the pipeline looks like, basically, well, normally you have some source of your data, a producer, you have some destination for your data, a consumer, you have some of those steps in the middle that do something to your data, and you have the data that flows from the producer through the steps to the consumer. And now if you think of this scenario, what can go wrong here? I already revealed this, because the problem can be when the consumer, so the party that resides downstream, is slower than the party that resides upstream, because then there is some excess data and you need to do something about it. So what can you do? Well, you can drop the excess data, which may seem strange, but actually this is a very common solution in a lower level of software and hardware that we not normally deal with. But if you take networking hardware, for example, this is something that often happens there. You can also block, so the party that is not able to cope with the data that is coming from the upstream can just block, but this is actually not what we want, because we want to behave asynchronously, we want not to block actually, so blocking before we process the next part of data is actually not the solution. Another way to deal with it is to buffer the data, either on the consumer side or the producer side. But if you think of it, well, it may not always work. I mean, if the differences in velocity are small, then buffering is probably fine. But if the difference is huge, then you need to remember that the buffers sit in your memory, the memory is limited. So if the producer is very fast and the consumer is very slow, the buffer will be exhausted basically, and you're going to have some kind of out-of-memory exception. So the way we deal with it in the Reactive Streams approach is called backpressure. Backpressure is basically a way of signaling or propagating demand from the downstream to the upstream. This if you think of like data flowing from the producer to the consumer, you can think of backpressure as data or signals coming like up the stream, so from the consumer to the producer. You can also think of it as basically propagating demand upstream. And what is very important here when it comes to backpressure is the fact that it is propagated from the very end of the stream to the very beginning. So for example, if you take the scenario that we'll be looking at today, reading data from files and then storing them to the database, then when the database becomes the bottleneck and it cannot cope with a lot of data that is coming from the files, the demand is propagated through the entire stream up to the point where the data is read from files, and the file reader is actually the thing that is going to slow down then. So it's not only notifying the previous step in the pipeline, but it's actually notifying up to the very beginning of the stream. So this architecture here, it's about stream processing with backpressure, but it doesn't already make it a reactive stream. There are some more criteria that a reactive stream needs to meet. First of all, well, everything needs to be asynchronous because we want to process the data in a non-blocking fashion. But also the back pressure itself, the demand propagation mechanism needs to be asynchronous and non-blocking as well. Because if you had a non-blocking processing of your data, but the back pressure was blocking and synchronous, well, it should still be synchronous and blocking anyway. And the goal of it, of course, is to reuse the resources whenever you can do it. So if you don't need a resource like a CPU core or a thread or anything, you're putting it back to some kind of a pool so that it can be used by other things that need it, and you're just not holding it for doing nothing. Another important thing about the reactive streams approach is that if we have a domain model or some representation of the stream, in this domain model, we have the notion of the fact that the consumer can be slow. I have two examples for that. One is the Twitter API. So if you take the Twitter streaming API for streaming your tweets from a given hashtag, for example, then if you connect to it, Twitter is allocating some kind of a buffer on their side, and it keeps sending you data. But apart from sending you data, it's also measuring the velocity, so how fast you consume that data. And if it detects that you are consuming too slow, it starts sending you, instead of the data, some signal messages that tell you that, hey, you're consuming too slow, and if you don't speed up, I'm going to disconnect, basically. Now, it's not really about how this is implemented inside, but the important thing is the fact that we have some representation of the fact that something can be slow. So if you go through the documentation, you already have the notion of the fact that we deal somehow with a slow consumer here. Another example is one of the built-in stages in Akka Streams. So stages are the things that process your data. This stage is called conflate. And what conflate basically does, it enables you to somehow handle the fact that the downstream is becoming slower. So conflate monitors the downstream and monitors how fast it is processing data. And you can provide a function that does something to your data, for example, an aggregation or just dropping the data and sending the last element, for example. And this function is applied when it detects that the downstream is slow. And then, when the downstream becomes fast enough, once again, it's going to send that aggregated data once again. And as I said, here also it's not really about the implementation details, but this is about the fact that if you go through the docs and you're looking at the built-in stages, you actually have some information that yes, we know how to handle that something is slow. So this is also really important in the reactive streams. Now, if you haven't used Akka Streams before, Akka Streams is one of the implementation of the Reactive Streams manifesto and the Reactive Streams concepts. Basically, what you do with Akka Streams, you have some built-in components that let you build a graph. A graph is the thing that is going to process your data. And the blocks are reusable, so you can basically define a small block that does one thing with your data, and you can reuse it somewhere else. An important thing about the graph that you build with Akka Streams is that it's lazy until you actually run it. So what you're actually doing when building this graph is preparing some recipe to process your data, but it doesn't do anything until you explicitly tell it to run and and you connect it to your data and actually run it. So this is just writing lazy recipes. So we have three kinds of basic blocks in Akka Streams. One of them is a source, and source is basically the producer of data, so it has a single output that sends the data. Then you have a flow, which you can call a processor, and the flow basically has one input and one output, and it does something to your data. This is a bit simplified because there are flows that can have multiple inputs or outputs, but this is the idea of a thing that can accept data and produce it somehow. And the terminating element of your pipeline is called a sink, or you can call it a consumer as well. So this is the part that has a single input and the data ends up there. So now let's have a quick look at the use case that I'll be covering today to show you how you can use different connectors in Akka Streams. So we'll start with CSV files that have some kind of ID and a value, and we're going to be tailing those files. Then partitioning by ID. So we actually want to check whether the ID is even or odd. And when it is odd, we're going to send it to some HTTP server that will be running in the background. And when it's even, we're going to send it to some kind of a database. Here it's going to be Cassandra. And this is going to run constantly. So the file will be tailed constantly. If we append something to it, then it will be processed accordingly. So let's now have a look at the code and how you can actually implement it. So we're starting with some boilerplate. We have our data model for the CSV lines with ID and the value and the strange constructor that takes a list, but it will be useful later. We have some settings to connect to our file, to connect to our database, but they are not really relevant here. So now what we need to do is start building our pipeline. So we'll start with the very beginning. So with the source, we need to tail the files. So I'll start with a source, because this is the party that is the beginning of your pipeline, Akka Streams. And you can see that source has two type parameters. And actually, if you looked at the previous slide, there was one type parameter to the source. Here there are two. Well, the first one is pretty obvious because this is the type of data that is going to be emitted by the source. And in our case, it's going to be a byte string. Byte string is basically a data type that wraps an array of bytes. It has some performance advantages. It is this comes from Akka, so it's not from the JDK, but from Akka Streams. But you can think of it as a byte array, basically. But there is also this second type parameter called mat, which stands for materialized value. What is a materialized value? So if you think about the components, the sources, flows, and sinks, they are sending some data between themselves. So, for example, this source is going to emit byte strings that will be sent to the other parts of the graph. But also the stages are able to, let's say, emit something to the outside world. So you want to be able to take a value from the stream and be able to read it outside. And this is what the materialized value is used for. So you can basically define a type of value that would be not sent downstream, but emitted to the outside world, and you can do something with it. But in our example, we won't be actually doing anything with this data, so we're going to use a special data type called not used. Why not used and not void, for example? Well, the reason is that Akka Streams is a library that can be used both in Java and in Scala, and those two languages have different notions of not returning anything. So in Scala you have units, in Java you have voids, and to be able to unify it, Akka gives you the not used type. And apart from unifying the type systems, let's say so, from Java and Scala, it also gives you the clearly gives you the intention, so that we are actually not using this value. So that's why another type is here. So let's call it file bytes, and here we are going to use the first connector from Alpakka. Sorry, this is a file tail source. So this is a source that lets you connect to a file. It needs a couple of parameters to its factory method. Well, first is the path of the data. The second is the max chunk size. So the chunk size is the length of the line. Our lines are pretty short, so I'll just put 100 here to be safe. Then you have the starting position. If you want to begin from the start of the file or not, we'll do it from the start, so it's 0. And polling interval, so how often do you read from the file? We're going to read every single second. So this is our first component of the pipeline that we implemented using an Alpakka connector to tail the file, which is the file tail source. So the next thing after reading the bytes from the file is to actually convert it to our domain model. So to convert it to the domain model, we need a component that would have an input for the file bytes and an output for the model. So if we need an input and output, then it's going to be a flow. So this is a flow that takes a byte string, because this is what is emitted from the source. Then it emits the model values, so this is the class from our domain model. And then once again, we are not going to care about the materialized value, so we're just going to use not used here. And let's call it toModel. And now we have another built-in component for parsing CSVs, which is also a part of Alpakka. It's called CSV parsing. And we have something that is called the line scanner. So if you look at the types, this is a flow that takes a byte string and returns a collection of byte strings, actually. So basically what it does, it splits the line and returns the collection of the values that are in the line. So in our domain model, we have the constructor that actually takes not a collection, but a list of byte strings with the field. So the first thing we need to do here is to actually convert this collection of bytes to a list. So we do it with a map method, and this is like some of the functions, some of the transformers that you use in Akka Streams, because this is a map from Akka Streams, it's not a map from Java Streams, for example. But as you can see, the API is pretty similar. So you still have a map method, you need to provide a function, and this would do something to your data. So we can use the list copy of method to convert it to a list. And then we once again we want to map it to convert it to our domain model. So we have a constructor that takes a list, so we can basically use the constructor here. And this is our simple flow that takes the lines from the file as a collection of byte strings, then converts it to our domain representation of those lines from the CSV file. And here we use the flow, so something that has an input and has an output. So the next thing is to define the destinations for our data. So we'll start with defining the sinks, so the things that are going to accept the data and send it either to the HTTP server or to Cassandra. And eventually we're going to implement the partitioning logic, because so far we are reading the data and converting it to our domain model. We'll tell Akka Streams how to send it to HTTP, how to send it to Cassandra, but then we'll still need to partition it somehow, and this will be the final step. So here, actually, we need some more logic. So we're going to define those as functions that will be executed once, and that would create those sinks. So in both cases, it would be a sink that takes a value of type model, so our domain model. And here we'll be discarding the result of the processing. So we're not going to use the materialized value from the sink. We're only caring about the fact that it actually got processed somehow. So we'll start with the HTTP sink. And now, well, before we build the actual sink, we need some way to connect to the HTTP server. So we'll do it using a flow. So this is also something that is well, it's not actually a part of Alpakka, because this is Akka HTTP. But Akka HTTP is what you actually use with Akka Streams when you want to connect to the HTTP server. It's a separate project, so technically it's not a part of Alpakka, but this is still how you do it. So basically, you can already see here that it's going to be backed by an actor system, as most of the things in Akka are. And we're basically creating a connection to our server URL, and this is a permanent connection that will just be there. And this entire thing, if you look at the type, is going to be a flow. So basically it will be accepting data. It would actually also return some data, but we're going to discard it. So for the sake of simplicity of this example, will not be taking these completion stages, but just putting data inside that flow. And actually in a second we'll convert it to a sink, because we want a sink here. So let's call it HTTP connection flow. And now we need to build the actual sink. So to build the sink, what we can actually do is start by building a flow, and then connecting to it to a predefined sink. So when we start with a flow and connect it to some built-in sink from Akka Streams, then the resulting type of this would actually be a sink, so something that will just swallow our data. So to build a flow, we start with the flow of factory method, where we can pass the type of the input data. So this determines the input type of the flow. And then since we want to send it to an HTTP server, we somehow need to convert our domain model data to an HTTP request. So we're going to do it with the map method. And here we're building a post request to the HTTP endpoint. And we need to put the value from our domain model into the entity. So we're just taking m value here. And now, when we converted our model data to an HTTP entity, we actually want to send it to our connection flow, the one we defined above. And for this, we are using the via combinator on a stream, which basically lets you connect your stream not to a built-in component like map, for example, because map actually also uses a flow underneath, but this is a built-in one that has a dedicated method. And if you have your own flow that doesn't have a dedicated method, you just use the via combinator and put the flow here. And now, since you want to discard the things that are returned by the connection flow, we're actually connecting it to a special sink called sink ignore. And what sink ignore does in Akka Streams is it basically takes the data and, well, you can say that it's just swallowing it. The only thing it does, it will report completion of the data processing. So it won't do anything to your data, but it will tell you when it's done processing it. So once again, what happens here is we basically, after having defined this flow for our permanent HTTP connection, we are starting with a flow that takes the values from the model, then we are mapping them to HTTP requests. Then having those HTTP requests, we're sending them through our connection flow, and we're connecting it to the sink that just ignores it and basically will accept the data. And then, thanks to it, the return type is a sink here. So this is how we connected to HTTP. Now it's time to connect to Cassandra, and we'll do it in a pretty similar fashion. So once again, we're defining a sink that takes the model values and has the materialized value of not used. It's going to be called a Cassandra Sink. And here, once again, we need some boilerplate to actually connecting to Cassandra. So first of all, we need to create a session, which is done with the Cassandra driver, basically. So we need to choose a host, we need to choose a port and connect to it. And this is our Cassandra session. And now we'll be executing some insert statement to Cassandra. We don't want to like compile it every time, so we want to prepare it and use it as a prepared statement. So we can say session prepare, and then we have a constant for our insert query to the database. This is going to be our prepared statement. And then also having, since this is going to be running constantly, we have our prepared statement, but we also need a function that is actually going to bind values from our model to this statement. So we won't do it once, like the function will be executed every time a value is inserted. So we'll need a function that takes a value and takes the prepared statement. And this function will be very simple, because what it would do is say, statement, bind, and the value here. Now I will cover that in a second. Let's call it a statement binder. And actually, we're not able to use a var here because this is a function, and like you can use var for the things that are local to your method, but not for functions. So for when defining functions with values, you actually need to be explicit about the type. So you can see here the actual type of our function. It takes two parameters, a string and a prepared statement, and gives you something that is called a bound statement. So now we can actually use the Alpakka component for connecting to Cassandra, which is called a Cassandra Sink. And it has a couple of parameters when we create it. First is the parallelism, so the number of queries that will be done in parallel. We'll put 1 here. Then we need the prepared statement. We need the statement binder, so the function that is actually going to bind parameters. And we need the session here as well. So we'll call it Cassandra Sink. Yeah, and then having this Cassandra Sink, we will apply a similar approach as we did with HTTP. So we're going to create a flow that will take the values of type model, then extract the actual value from it, and connect it to this sink. So we're once again starting with a flow of the model class. Then we're just using map to extract the value from it. So it's from m to m value. We don't have a getter for it, so that's why no method reference here. And actually here it's a bit simpler than in case of HTTP, because we already have a sink. So in case of HTTP we had the connection flow, but here we already have the sink that connects to Cassandra, so we can basically only use the to method and provide the Cassandra Sink here. So once again, what we did here, well, first of all, we had some boilerplate to create the connection to Cassandra, to create the prepared statement, to define the way of binding values to our prepared statement. Then we used the actual component from Alpakka, the Cassandra Sink, to actually be able to send values to Cassandra when they arrive at our sink. And then we're using the approach that is similar to the one we had in the HTTP connection. So we're creating a flow that takes values of our model, maps them to their actual values, and then connects it to a sink. So now if you look at the components that we already have, well, we have the source that reads from the file, we have the transformer, the flow that transforms to our data model, we have the sink for HTTP, for Cassandra, and the last thing we need here is the partitioning sink, sink. So that would actually do the partitioning and send the data where it should go. So let's write it. It's going to be called we need a type as well. So this is also a sink that takes a model, has the materialized value of not used. It's going to be called partitioning sink. Yep. And here we're going to use a bit different approach. You can say that this is maybe a bit more low-level approach to building a custom component of your graph using something that is called GraphDSL. And GraphDSL is basically another way to define parts of your graph. So before we used the flow factory methods to create a flow. Here we can use the GraphDSL to define something more complex. So this is a create method, and the create method takes something that is called a builder. And the builder is a thing that you actually use to add things to your graph, to connect them together, because the partition thing will have one input, but it would have two outputs, so we would need to somehow wire it to the HTTP sink and to the Cassandra sink. And that's why we're using GraphDSL here to be able to do this like lower level manipulations. So when using the builder, you need to explicitly add everything to your graph that you're going to use. So, well, first of all, we'll be using another built-in stage from Akka Streams, which is called partition. And when creating a partitioning stage, well, you can provide the type that you are expecting as the input. Then you provide the number of outputs. In our case, it's going to be 2 because we are only testing for even and odd. And then you need to provide the function that is actually going to do the partitioning, so decide which to which output the value is going to go. So in our case, it's pretty simple because we just take the ID from our model and take the remainder from division by 2. And we're going to call this graph element partition. And now, in a similar way, we need to explicitly add the two of the sinks that we defined previously, so the HTTP sink and the Cassandra sink. So we're going to say builder add, the first one would be the Cassandra sink, and let's call it Cassandra. And similarly, we're going to add the HTTP sink, so it's builder add HTTP sink, and it's called HTTP. So here you can see that we're calling the methods that actually create our sinks. It's important to remember that they don't do it. They don't do anything yet with the data because we haven't run it explicitly so far. And now what we have in our graph is like the partitioning component with 2 dangling outputs and 2 sinks that we want to connect to it. So we need now to do the connections explicitly, also using the builder. So now we want to say that from the first output of the partition stage, so from the output with index 0, we want to take the data and connect it to Cassandra. So it's remember that the thing we use here, it's not the Cassandra sink that we created, but this is the thing that we added to our graph. So this is the output of calling builder add. And in a similar fashion, we would add the HTTP sink. We just take the second output, so with index 1, and we connect it to HTTP. Now, this is because so far you may have noticed that the DSL here is pretty nice, although this is Java, not Scala. But this is the place where actually, if you were using Scala, the DSL would be a bit nicer because you would have something like tiled arrows that you would be able to use to basically draw an arrow between, for example, the partition and HTTP. In Java, you cannot do it, so this is one of the few places where the Scala DSL is much nicer. But apart from that, you could notice that the Java DSL is pretty nice. At least I think so. So now what we did was connecting the 2 sinks to the outputs of the partition stage, but we still have a dangling input of the partition stage, of the partition flow. So what we want to do with it is to expose it to the outside, because eventually we want to create a sink that is going to have a single input, and actually this input is what should be connected to the input of the partition stage. So what we do here is to return something called a sink shape of, and here we say just partition in. And this means that the thing we are returning is going to have the input of the partition stage exposed as the input of the sink that we just created. You can see that something doesn't compile here, so let's see what it is. And actually the problem is that we are, in the definition of the method, we define the type as a sink, but what we're returning here is a graph. And this is one of the things that are like a bit complicated in the APIs of Akka Streams, because basically all the components of the graph, like a source, a flow, or a sink, are actually graphs with a given shape. So, for example, a source is a graph with a shape of a source, and a sink is a graph with a shape of a sink. And actually what we need here as the type is not a sink, but a graph that has a shape of a sink. So we need to change a bit here. So we just put in graph here. And here we're going to tell it that it has a shape of a sink. So this is pretty similar. This is a bit lower level. That's why we need to use the other ties, but it still makes sense. So we have a graph that has a shape and a materialized value. And instead of just using a sink, we use a graph that has a shape of a sink, so a single input, and it has some kind of materialized value that we are not using. Okay, so now we have created all the components for our pipeline. So we have the thing that reads from files, we have the thing that transforms it to our domain model, and we have the big partitioning sinks that internally has two other sinks connected, and it decides what to do with the data and sends the data accordingly. So now it's time to assemble the entire pipeline together. Please remember that it doesn't do anything yet because we didn't run it still. So let's create a method to actually run it. And this is pretty simple because we'll be basically assembling the pipeline from the three components that we have using the via and the two combinators that you've already seen. So we'll start with the source, the file bytes. Then we want to connect it to the toModel flow that converts it to our domain model. Then we want to connect it to the partitioning sink. And eventually we need to run it. And you can see that there is a parameter required to the run method. It's called a materializer. So what is a materializer? Basically, it's something that provides the runtime for your graph to be executed with. And what the materializer does, it actually tries to optimize your graph a bit. It also checks whether there are no dangling inputs or outputs. So for example, if we didn't perform the step here of connecting the outputs of the partition and we left a single output of the partition stage not connected, the materializer would complain about it at runtime. There is no way to verify it at compile time, because at compile time you can only verify whether the types match. But this is going to be verified at runtime, and the materializer would tell you that, hey, you have a single output of the partition stage that is not connected to anything. And the materializer here is based also on an actor system. Now the last two methods that we are calling here, the two with a sink and a materializer, are used so often in combination that actually there is a shorthand for that, which is called run with. And here you can basically provide both the sink and the materializer in a single method. So it does exactly the same. It connects to the sink and then does the run, but you do it so often that you just can do it a bit shorter. So now the last thing we need is a main method to actually run it and to check if it works. So here's our run method, and now let's try to verify our solution. Okay, so we have a couple of things here. We have a constantly running query on our Cassandra. We have our HTTP server that will be running and accepting connections and data. And here we're running the CSV importer. And we had some data in a file that I didn't show you. It's called data CSV. So it has like 5 values here. And you can see that actually the values were processed. So some of them went to the even ones went to Cassandra. The odd ones went to the HTTP server. And now we can see that if you run another odd value, for example, it's still going to the HTTP server. If we add another even value, it's going to go to Cassandra. So the pipeline that we assembled and that we run is running constantly. So it is still monitoring the file with the polling interval of 1 second that we defined. And basically, it keeps the connection to the server and keeps processing the data. Okay, so that was that for the code. Of course, as to everything, there is also more to Akka Streams and to Alpakka that you can do. You've already seen the DSL for constructing some less trivial graphs. There is, if you want to see how to use the Akka Streams with Java with some other examples than here, I recommend to read a blog post that I wrote some time ago. There is also an even low-level API for creating your graph components, even lower level than the graph DSL. So coming from the top, when it comes to simplicity, you have the built-in stages like map, for example. Then you have the graph DSL, which is a bit lower level, and then you can even directly use the Akka Streams API to build your own stages that, for example, have a state inside. Because there are some built-in stages that can hold state inside, but most of them are stateless. But you are free to, if you do it carefully, you're free to write your own stage that holds some state inside and aggregates things, for example. And this is also a good time if you would like to go into open source to become a contributor of something, because Alpakka, as you've seen, is not very well known yet. It doesn't have a lot of connectors, well, certainly less than Camel has. Actually, just like a month or two ago, it was released in version 1.0, so I think you can consider it ready for production use. We actually do it, and it works. And basically, if you wanted to become a contributor, you just take the connectors that Camel has and Alpakka doesn't have. You take the diff, and you can implement anything. They actually have pretty nice guidelines how to do it and how to properly write a connector with all the back pressure support and stuff. So that's all I had. I'll now switch to the questions, if there are some. So I thank you now for your attention, and then I'll thank you later, and let's see if there are any questions. Okay, so the first question is, does everything has own back pressure? Can we choose different strategy of back pressure in everything? So, well, the built-in sinks have their back pressure mechanism defined somehow, and as far as I know, you can't really influence it. But if you write your own sink, then you're basically, if you use the very low-level approach to writing your own components using the Akka Streams APIs, then you basically have control over the methods that are fetching data from the input. So then you are basically free to apply any back pressure strategy that you'd like. So then you are completely flexible, basically. What if we cannot slow our source? For example, we have a process that produces stuff on its own, and we don't control it at all. Then probably I think you would need something that is connecting to your process and does some buffering. Of course, as I said at the very beginning, buffering has limited applicability here, because if there is too much data, your buffer is basically going to explode. But perhaps you can do something like either buffering or, for example, using the conflate stage that I showed you as an example of how slow consumers are represented in the domain model. And if there is really a lot of excess data that you're not able to deal with anyway, you basically may need to either aggregate it somehow. I mean, if there are numeric values, then you can sum them, for example, or maybe you would need to just drop the data. So basically just to emit the last element or a couple of the last elements. So if you have the process that is not really reactive and you cannot apply back pressure to it, you would need to put something in between this process and your reactive pipeline, because otherwise, yeah, it won't have a way to work. Okay, I don't see any other questions here, so thank you once again for your attention and enjoy your lunch.